So first, let me start by thanking the organizers for the wonderful conference and the scientific committee for the opportunity to talk. Let me also say that this is joint work with Ivan Liberty and Peter Lumsden. And so, as you can see from the title, this talk is about the relation between Toposes and Localic Groupoids. So let me start with some context, really. So, when Grothendieck introduced Toposes, they were seen as a generalization to topological spaces, but at the time it wasn't clear exactly in which way they were so. But then Joel and Kearney gave a precise notion clarified this in saying that there were two steps to this generalization. First, that you need to move away from the idea of points, that you go from topological spaces to locales, which are mild generalizations of topological spaces. But then that's not quite enough. You need to then consider somehow adding automorphisms as well, which is another way to say that then you work with groupoids in this category of spaces, of localic groupoids. And so precisely they proved what you might call a representation theorem, that every topos is equivalent to equivalent sheaves on a localic groupoid, right? And so the talk is about these representation theorems, but there's also a related notion that I want to discuss that are present in the literature. We might call them covering theorems, which essentially state that every topos can be covered in an adequate way by a locale. And these are closely related to the representation theorems I was mentioning before, but they also have they're also useful in their own sake, because you can use them to get tighter completeness results. For instance, Arodi does this when proving topological semantics of lambda calculus. All right, so let me maybe give just a selection of papers from the literature that illustrate that there are many such, that this is something that has been studied a lot. And for instance, so I won't go through each one separately, but the first two I think of them as more covering theorems, essentially saying that from a topos you can cover it from a locale, whereas the last four are maybe more in the flavor of representation theorems, which maybe the last one being a little more refined in that, because it's actually a duality. And so this, so we will try to abstract the notion of reconstruction theorems and covering theorems, but theorems more refined like this will not quite be in the scope of this work, but I wanted to mention it nonetheless. So yes, so the precise goals for today is that we would like to introduce a framework which somewhat abstracts and unifies some of these theorems from the literature, and then a way to present these by minimally, so with a rather concrete data of just a locale, so a general space, and a sheaf over it, which satisfies some properties. And then at the end, assuming I still have time, then I will discuss a little the logical side of the story, which allows you, lets you recognize some of these concrete data. All right, and so of course I have some background to go through, and so here's the idea of locales. So you're all familiar with topological spaces, and there you probably know also that the open topological spaces are special kinds of ordered sets, partially ordered sets, that they're what we call frames, meaning that we have arbitrary unions and finite intersections, and that the two distribute over each other distribute over each other. And so when you abstract that, you get the notion of frame. And another way to state what the topological space is that you just have a set of points and then a subframe of the frame of subsets of X. But when you consider locales, you let go of the idea of points, and so you just consider the frame, right? And concretely, then you want to look at so you could work with locales just as frames, but we want to keep the geometric direction, meaning that we consider locales just as the opposite category of frames. And I have just a small remark here to convince you that this is a rather mild generalization, in that you can, even the locales don't have points to start with, you can still get a topological space from a locale, and of course every topological space gives rise to a locale, and if you, and they're related by this adjunction, which happens to be idempotent, so if you're happy to restrict to the fixed points of this adjunction, you could not even see the difference, but they are a different object. Right, and so also locale obviously equals related to toposes, and the reason you need to go from let go of the idea of topological spaces and move on to that of locale is that actually, if you remember the sheaf condition on the sheaf axioms for on the topological spaces is actually defined on its underlying locale. You don't need the notion of point to define it, so it's much more natural when you're dealing with toposes. By the way, I didn't say it, but every topos, I'm concerned, when I say topos, I mean quadratic topos in this talk. And so the form taking sheaves on the locale gives you a way to say it as a topos, and it happens to form a reflective subcategory of toposes. And there's another, of course, the notion of frame or locale can be done internally to any topos. And in this way, if you take internal sheaves on an internal locale, then you get a topos over the topos EU we're doing this in, and the maps that arise in this way we'll call localic maps of toposes. So this is another way to phrase it, that internal locales to correspond to maps of toposes into a data localic. And here are the few facts that I will need for the rest of the talk, that if I look at the diagonal of a topos, that's always a localic map, and that these maps are closed by under pullback in composition. Also, so here I need to introduce two classes of geometric morphisms. I just have the definition. I'm sure you've all seen it before, but the point is that I want to remind you that a geometric morphism is called surjective if the inverse image is faithful, if it's open, if the inverse image preserves the universal quantification. And then there's a strengthening of this two notions, that a geometric morphism is connected if the inverse image is not only faithful but fully faithful, and also that it's locally connected if the inverse image preserves not just quantification but arbitrary pi types. And so the other fact that I need to, that will be useful for the rest, is to know that the class of open surjections and connected locally connected maps are both closed-dotted pullbacks. Okay. So as I said, we will be looking at Localic Groupoids. So I have here the definition of an internal groupoid in a category, and generally this forms a two-category of internal groupoids. And in the case where the ambient category is locales, then these are called Localic Groupoids. And here's an important example, is that if you have any map from E to B, then you can take its pseudo-kernel, which is a generalization of the usual kernel pair from one category theory, where then you take the check nerve, which you truncate one step further than in the usual case, and this forms an internal groupoid. All right. Okay, so now we have internal groupoids. We need to take, at the end of the day, we want to be able to say what is a sheaf of such an object. And so in general, if I have an internal groupoid, I can talk about an internal pre-sheaf just by internalizing the usual definitions. But then it's easier to do so when using the definition of saying it as a discrete vibration rather than as a map into set. But yeah, that's rather common when doing internal category theory. And so, yeah, you have the total map over this object of objects, and then an action morphisms that is given by this map, and then you have obviously some axioms to satisfy. But so that's the general definition in a category E. But when we are dealing in, when E is the category of locales, then you can ask for a further condition. So you have still, so what the definition of an equivalent sheaf is that of an internal pre-sheaf, and then you ask further that this total map here is étal as well, meaning that it corresponds to a sheaf on G0. So another way to phrase this is that it's a sheaf on the localist G0 with an action, a compatible action of G1. All right. And so in this way, you get the topos, which is usually denoted B of G, which actually assembles into a functor in this way. And so, yeah, this is the point. For instance, so this is what we'll be studying today. And there is also an important remark that was proved by Mordijk, is that you can recover this topos of equivalent sheaves by doing a pseudo-colimit in the two categories of toposes, where you first take the internal topos in locales, apply sheaf pointwise to it, then you get a diagram in the category of toposes, and take the pseudo-colimit there. And that's another way to describe this topos, which is useful because it's a more categorical description of it. So the two are important, but this is useful for this work. And lastly, before we get to the main section, I want to remind you maybe what are more present of descent types in the category of toposes. So you'll remember that in general we said that an epimorphism is effective if it is a co-equalizer of a kernel pair. Well, you can do this. You can generalize this definition by saying that in the category of toposes, if I have a geometric morphism, I can take its pseudo-kernel pair and then the pseudo-colimit of that. And if I recover the same topos F, then we will say that the map we started with was of descent type. You probably have seen this in the literature as effective descent type, but we prefer the terminology descent and with descent, but this is just an aside. And let's see. So yeah, important examples that were also proved in this paper of Joel and Kenny, that open surjections are of descent type, and in particular connected and locally connected morphisms are as well, because they are a special case of open surjections. And now this is a definition that we introduce here, that we will say that a geometric morphism is of locally the stable descent type if it is of descent type, but also each time I pull it back along a localic map, it's still of descent type. And this will come in rather quickly. So now we can go to the main section. And so typically when we have a reconstruction theorem in the literature, it's not defined intrinsically on toposes, but if you want to get a localic groupoid presenting a topos, you usually have to add in some extra data, and usually this takes the form maybe of a site or something like this, or of a bound. And so this is also something we need to do when abstracting the situation. And here we chose to work not with the notion of a site, but with the notion of a pre-bound, which is closely related to that of a site. So a pre-bound is an object of the topos, where if you look at its sub-objects, that is a generator of the topos. And they are related in the sense that if you have a site, you get a canonical pre-bound, and from a pre-bound you can extract the data of a site, but they're not like you have sites that don't come from a pre-bound and in general. So, but this is a related notion of extra data. And let me remind you that in the category of toposes, we have a rather important example, that the classifier of the theory of objects, which is just the preshift topos of the opposite of the category of finite sets, which has the important property that maps from an average topos E into it corresponds to objects of E. And the reason I'm reminding you of this now is that this allows us to give a neat definition, a neat characterization of the notion of pre-bound, namely that if I have an object of the topos E, it is going to be a pre-bound precisely if the corresponding element, the corresponding geometric morphism from E to Ceto is localic. Right? So if we want to work with the category of toposes equipped with a pre-bound, we might as well work with the slice here of toposes of a Ceto, which are localic. So it gives us a nice category to work over. And so then we can, so the reconstruction theorem, broadly, this is you take a topos E and you get a localic groupoid that presents it. But now if we want to abstract this, we will make the following definition that of a reconstruction functor. So you have your category of toposes equipped with a pre-bound, and we ask for a pseudo-functor R into the category, the two categories of localic groupoids, such that when I go back down to the category of toposes by taking equivalent sheaves, I get back the topos I started with, not with the data of the pre-bound, but and the way to make this concrete is to say that this triangle commutes up to natural equivalence. All right, and so I said there was a related notion that of covering functors, and here the idea is not that you get a localic groupoid, but that you get a cover, a localic cover, meaning a map whose domain is localic, is a locale, and that it has a property that this is of the same type. This is a nice notion of cover. And then again, we can abstract this definition by saying that now I again work with the category of toposes as equivalent pre-bound, and the covering functor D would then not go into the category of localic groupoids, but of map of descent type whose domain is localic, and such that when I go back to the topos, I have the same commutativity condition up to equivalence, and now we can go to the notion, the minimal notion I was talking about earlier, is that the claim is that both of these notions can be reduced to much more concrete data, which is what we call an amorphous sheaf. And so that's simply a locale, call it Q, and a sheaf F over it, so that when I look at the corresponding map into Seto, this is going to be of locally stable descent type. And so, yeah, I think we can all agree this is definitely more concrete than a big sort of functor in the category of toposes. But before we see how we can recover the notion from this, let me just remark that if, for instance, because in general, verifying that a geometric morphism is of descent type is not always easy. Let me remark that if we can instead show that this corresponding map is an open surjection or a connected locally connected map, then it will follow, because as you remember I said that both of these classes were of descent type, but also stable by pullback, which means they're even more stable than locally stable. So now let's see how to get how to recover convex functors and reconstruction functors from amorphous sheaves. So first, to get a recovery functor, then the idea is rather simple, is that if I have a topos E and I want to get a cover of that topos, I have a topos E together with a pre-bound of E, which is a localic map into Seto, and I want to get a cover of this topos E, I can then simply pull back the map F bar that we had on the previous slide, and now we can check that this will have the correct properties, because this is of locally stable descent type, and I know that L is a localic map because it corresponds to a pre-bound, and so when I pull it back, this will still be of descent type, and also this is a locale because when I pull back this localic map here, it's still localic, but it's localic over a localic topos, so the domain is localic, is a locale, so that's exactly what we wanted. And the fact that this is defined by pullbacks means that it will have the right functorial properties. And now, to get from a covering functor to a reconstruction functor is also rather categorical. There's a few steps I need to go through before that. The first is that I need to check that if I have a geometric morphism whose domain F is actually a locale, then when I take its pseudokernel, what I get is actually a localic groupoid rather than just a simple shell object, autocratic simple shell object into category of toposes. And there, what I simply need to show is that, so remember that the so-called pseudokernel is these iterated pullbacks. So if I can convince you that these iterated pullbacks are still localic, then that will suffice, because we have seen that the sheaf functor from locales to the process is reflective, so it reflects limits, in particular these pullbacks. And then again, this is rather direct, because we know that the diagonal of a topos is localic, which means that when I pull it back to get this pullback here, this map here is still localic, and we knew that F was localic, so the product of F with itself is still localic. And so again, this is localic, and as I said, this is enough to get this property. And so in other words, what we get now is that we get a pseudo functor K defined in this slice of locales of the Toposes, which is the restriction of the pseudo-kernel functor into Localic Groupoid. And here, so we can use this functor to get. So let me start from the back. Maybe that here, what we have this triangle here is just saying that if I have a map of Toposes, a geometric morphism, I can take its pseudo kernel and then its colimit, and then in general I won't get back the same thing as the codomain of the map I started with, but there is a comparison morphism, and that needs not be an equivalence. But if I restrict that to maps of descent type, then this becomes an equivalence. This is precisely the statement of descent. And if I further restrict this to not only the maps of descent type, but those who have a localic domain, as we've just seen, then we land actually in localic groupoids. And so by restricting this triangle at the back, we get this front triangle, which is exactly what we need to go from a covering functor to a construction functor. Because indeed, if here I have my covering functor that takes a topos equipped to a pre-bound, gives me a localic cover of it. So this is the data of the covering functor, and then apply this. Then I can paste this triangle on the previous slide, and pasting these two gives me precisely the functor R, which would take a topos, gives me a localic groupoid, such that which has the right properties. And so, of course, then what we've seen is that from an amorphous sheaf we get a covering functor, and from a covering functor we get a reconstruction functor. And so you can compose these two things, of course, and you get that amorphous sheaf presents both these notions. Let's see, I still have a bit of time. So, So, for the logical side of this, let me remind you about classifying toposes. That in general, if I have any geometric theory T, I can look at, I can take models of it in any topos, and this is defines a pseudo-functor in the category of toposes. And this happens to be representable, representing an object being the classical topos. So this is just another way to say that maps into a set of T will correspond to models of T in the domain of that map. And in particular, this, if you look at the identity geometric morphisms, that gives you a universal model of this theory in that topos. And we've already seen an example before of the theory of objects, but you can have much more general theories. And this is useful to, we can use these notions to give a logical interpretation of open surjections. For instance, we know that if I have a single-sorted geometric theory and a map from the topos into a classifying topos on that theory, this map will be surjective precisely if the corresponding model of E is conservative for that theory, meaning that the properties it satisfies in E are precisely the one you can prove from T. And if you think about the way you interpret satisfiability in a topos of geometric sequence, it comes from the fact that you can always, these conditions cannot be always be reduced to checking whether a given map is an isomorphism, and being a geometric surjection is in particular mean that the inverse image is a conservative functor, so yeah, it's not that surprising. And then a bit more intricate maybe is that if you want to detect when a geometric morphism is open, you have to consider this full first-order theory of T. So because in general I have a geometric theory, so these are all about geometric axioms and entailment, and in general the criteria of classifying topos is not really about first-order logic. You don't have all the universal quantification, but we've seen that an open geometric morphism is one that preserves this universal quantification, and this is made precise in this paper of Professor Johnstone that's basically show that I can detect when a map from E to set T is open if I know that the model of T in E satisfies the same properties of the universal model of T in set T. The same first order properties. And so that allows you to check when a geometric morphism is open. So when you put these two together, you get a criterion to see when a geometric morphism into set T is an open surjection. And so in particular in that same paper, they compute the full first order theory for the theory of objects, which is this rather nice, funny theory, which if you look at the first two axioms, this basically says that the object is not a singleton. And if you look at this axiom here, in the case where phi is just false, bottom, then this says that it's not infinite either. Of course, there's a bit more generality because phi can be an incoherent formula. But yeah, it's. I mean, if you not use the constructive logic, this is maybe a bit surprising, but this is the. So the full first order theory for the theory of objects can be presented by these minimal axioms, and so then when we put the last two results together with this theory that they computed, we can detect when a geometric morphism into set tau is an open surjection, precisely when the model of the object of E corresponding to that morphism is a conservative model of that theory that was displayed on the last slide. And so, in particular, when I look at that for amorphous sheaves, this says that if I have my local Q and my sheaf operate, if this is a conservative model of this theory, the full first order theory of the theory of objects in this category of sheaves, then it will correspond to an open surjection, in particular to an amorphous sheaf. I'm not saying that this is an if and an if, but this is you can recognize some of amorphous sheaves by this, by a purely logical interpretation. Right, so just to summarize, to conclude, we have seen that covariant representative functors abstract versions of these of covariant representation theorems that are present in the literature, and then we've seen that both of these notions can be presented by concrete data, which are these amorphous sheaves, which is just basically a local and a sheaf over it. And then they're generated by general categorical constructions, which we sketched. And then lastly, we quickly saw that we can recognize some of these amorphous sheaves via logic. And before I finish, let me also mention related work about by Graham Manuel and Joshua Wrigley about representation. Again, about representing Toposes using Localic or tautological groupoids. If you're interested in this, if you're interested by this talk, you might enjoy these papers. And then I have some references. But thank you for your attention.
Comments or questions? Yes.
If you apply your functor from covering theories to representation, from covering functors to representation functors, to the Barbier-Conescu cover, do you precisely cover the Joyal-Tierney representation?
That's something we try to work out. We didn't finish all the computations, but I don't expect so, because if you look at the paper of Joyal-Tierney, the cover they start with is a different cover than the Diaconescu cover. Of course, it could happen that somehow you would get the same Localic Groupoids, but that seems quite unlikely. So since they start with a different Localic cover of Seto, you should get a different Localic Groupoid.
Steve.
What's a logical description of the amorphous sheaf in the case of say, classifying topos constructed as equivariant sheaves on the groupoid of models? As I'm sorry to say, I don't quite know. We haven't looked at it in that generality, but that's something we should do, of course. Okay, I have a proposal. It might be the structure sheaf from Spencer Briner's thesis.
Okay, I'm not familiar. I'll look at that.
So we'll just thank the speaker again. Sorry.
I was just curious about the name, amorphous
yes.
sheaf. I mean,
Right. This comes from this example because so if you think of it, the first, so you have the theory of objects, basically with no axioms, and then you get this different theory which basically says that your object can't, saying that it's conservative of the theory of object means that it can't satisfy anything interesting. It's sort of amorphous in this way because that's where it came from.
We can do it now.